Good morning, everybody. Today, we're going to move on and talk about one of my favorite topics, partial derivatives. Actually, you've seen this before. You've seen something very similar, and the rules are the same. In Calculus 1, you talk about implicit differentiation. So, for example, if we had an equation we had that equation using implicit differentiation. Now I said, find dy dx. The way implicit differentiation works is we have to take a derivative of both x and y, respectively. So, for example, in this first one, it's a product rule. So we take the derivative of the first one, leave the second one alone, then add derivative of the second one, leave the first one alone. But here's the difference. Whenever you take a derivative of y, you have to put dy dx. Because these functions are all functions of x. The derivative of x squared is 2x. Derivative of y squared is 2y dy dx, and one's a constant. So now we're solving for dy dx. We have to get them all both on one side, everything else the other side. So we have x squared here. We move this one to the other side. So we subtract 2y dy dx. And we move this one to the other side since it doesn't have a dy dx, minus 2xy. And to solve for dy dx, since they both have dy dx, we can factor those out. And divide both sides by x squared minus 2y. So our answer becomes dy dx equals 2x minus 2xy over x squared minus 2y. And that's implicit differentiation. Well, we're going to do the same thing today when we look at partial derivatives, except a few things will change. All right. That's an example of implicit differentiation. Let's look at, first off, we'll start off small. Partial derivatives of two variables. And that's what our function is going to look like. Now, remember, we said yesterday's class that if we have two variables, we actually have three because this is the z-axis. So let's work up to the definition of it. If x sub 0, y sub 0 is a point in the domain of the function f of x, y, vertical plane y equals y0, we'll cut the surface of our z value. In the curve of z. Because as we're talking about derivatives, we also have to talk about what it really means. And then again, the definition doesn't change. So what this looks like is if we had an XYZ plane, and we had a point X sub 0 and some other Y sub 0. This is that point. And the plane that's created from this function f of x, it could be anything. It could be a curve, it could be a circle, it could be whatever. So that is the plane up in the z range. This point projects up to some value on this plane, and it creates a line in there, a line along the curve, because this plane through YZ, remember there's a plane here, and it cuts through that. We're going to be interested at that point there, because now at this point there, since we're dealing with derivatives, what can we find there? Well, the derivative, remember, you can find the slope of a curve at a point. You can find the tangent line at that point, tangent to the curve. And by definition, also, the derivative is also a rate of change of the function at that point. Yeah, this is all what we derived, what we defined back in calculus 1, what a derivative was. It again extends forever, whether it's a 2-dimension, 3-dimension, or n-dimension domain. Since we're dealing with multiple variables now, as we saw in our ordinary differential equation, we have dy dx. When you use d, this defines an ordinary differential equation. In partial differentiation, our symbol now changes. So now we take partial derivatives. So whenever you see this symbol, we know it's a partial derivative. The big difference of that is in ordinary differential equations, whenever we take a derivative of y, we have to put dy dx. So if it was y squared, then we have 2y dy dx. But in partial derivatives, If we're taking derivative of this, then we just put 2y. All right. Because remember, when we have multiple variables, now, whenever you take a derivative of z with respect to x or y or whatever, yeah, then you have to put the derivative dz dx. dz dx. Let's look at the definition. The partial derivative of some function f of x, y with respect to, from now on, I'm going to WRT, just switch right. With respect to x. At the point x0, y0 is defined as this. The partial of the function with respect to x at the point x0, y0 is equal to the derivative with respect to x of xy at x equals x sub 0. Again, the process is the same, taking the partial derivatives as it is taking ordinary derivatives. It's just that when we first start off, our symbols change. Speaking of symbols, symbolic notation used in partial derivatives. So here, right now, for this first half, we're talking about with respect to x. So as we just seen, we take a partial derivative of the function with respect to x, and we have our variables at the point we're looking at. This is the same as this notation. The function taking a derivative with respect to x. With respect to x, because that's down there. Again, and since f is the same thing as z, we could just do the partial of z over partial of x at that point. So again, since we had f of x, y is the same thing as z. Yeah, so you have to be very careful on when you're given an equation, you're asked to find things, make sure that you observe what the denominator is or what the subscript is. Because you're going to see in a minute that we can have multiple subscripts or indices in there. When we have a specific point, x sub 0, y sub 0, where the partial derivative is being taken, partial derivative. I'm gonna start writing PD for that because it's too much to write. Becomes a function with a domain that is a specific point where the partial derivative exists. Again, this goes back to our definition of derivatives back in calculus 1. If a function has a derivative, it only exists if the function's continuous, the limit exists, the point of the limit exists, and they're the same as approach for both sides. So if we take a partial derivative and at every point where that partial derivative exists, that defines our domain. So again, our notations are very unique. So that'll be the hardest part, getting used to. Now, let's look at the slope of the curve of this function. At x, we're dealing with x right now. At the point P, x sub 0, y sub 0, and f0, y0. Because remember, if we have two dimensions, two variables in our function, we actually have three variables in our equation, because we have the independent variables and the dependent variables. So our point is a three-dimensional point. That's how come if we have three variables inside our equation and our dependent variable is a fourth, those are much more difficult, if not impossible, to draw. So the slope of the curve of this function at a point P in the plane y equals y0, because we're taking it with respect to x here, is the partial derivative of our function with respect to x at that point, x0, y0. So when we ask for a slope of the curve, just it's got to be specified, because now we're taking it with respect to x. So take a derivative of that, the partial derivative with respect to x, and plug in the values of that point, and that'll give you the value of the slope of the curve. Let's look at the tangent line to the curve at a point P. Again, it's the same x0, y0, f of x0, y0. So the tangent line to the curve at point P is the line in the plane y equals y sub 0 that passes, through the point P with the slope above. Again, this is all the same stuff we did in algebra and in calculus 1. Because if I asked you to find the slope in algebra. If we had a curve, what's the slope of the tangent line? Well, we have a point. Take the tangent of it. And the slope is at that point at x sub 0, y sub 0. The slope of that point of that tangent line is the slope of the curve at that point. Now let's look at the rate of change. The partial derivative df over dx at some point has a rate of change of the function with respect to x when the y variable is held fixed at the point y0. So in other words, y is equal to y sub 0. Well, all that says is to find the rate of change, also the slope. We find the partial derivative and set y equal to whatever the y value is, and that'll give us the slope of the curve at that point. Now, remember, when we deal with partial derivatives, we can take a partial derivative with respect to x, or with respect to y. So in other words, all these are exactly the same. But all we do is change, instead of x, now it becomes y. The definition: the partial derivative of some function xy with respect to y at the point x sub 0, y sub 0 is, now we change the y at x sub 0, y sub 0. So that becomes a derivative with respect to the y of the function. Remember, now, instead of x sub 0, y sub 0, I set y equal to a fixed point, and I take the limit of this function. So that's the partial derivative with respect to y. Again, it looks the same as a partial derivative with respect to x at the point xo, y0. But now I fix the x. So that becomes the limit as h approaches 0 of the function x sub 0 plus h, f sub 0 minus x sub 0, y sub 0 over h. Again, partial derivatives, by definition, remember, the definition of a derivative is, so the derivative of y was actually the limit as h approaches 0 of x plus h minus f of x over h. Because we only had one variable then. This is the original back in Cal 1. Now we have two of them. So the partial derivative with y, the y changes. Partial derivative with respect to x, the x changes. We just have to remember to do two different operations on the same function. One for x, one for y. And it increases when we have more variables. Let's look at the slope of the curve. These are going to be the same. The curve, it's going to be the same. Z equals f of x sub 0. Now, since we're dealing with respect to y, the y is fixed at the point P, which is x sub 0, y sub 0, f of x sub 0, y sub 0. The slope of the curve in the vertical plane is the partial derivative of x with respect to y at the point x sub 0, y sub 0. Okay, it's exactly the same thing, except instead of x, we put y. The tangent line to the curve at point P. Again, it's x sub 0, y sub 0, f of x 0, y 0. Is the line in the plane x equals x sub 0 that passes through P with the slope above, with that slope. And the rate of change of f with respect to y at the point x sub 0, y sub 0, when x is held fixed at x sub 0. So it's exactly the same thing, it's just they're reversed. So partial derivative with respect to y looks like this. Partial derivative of the function with respect to the partial of y at x sub 0, y sub 0 is the same thing as if we write that function, we're taking derivative of y at the point x sub 0, y sub 0, df dy, or we could just write fy. All of these mean the same thing. They all mean the partial derivative of the function with respect to that one variable. So we're going to do some examples in a second. Now let's go ahead and do some examples now. Here's the first one. Find the value of partial derivative of f with respect to x, and the partial of f with respect to y at the point 4, -5, if the function equals that. Our point is 4, -5. So the first thing we have to do, let's look at the partial with respect to x. Since we're looking for x, y is a constant. So take derivative of this function with respect to x. So it's x squared becomes 2x, 3xy. So this one is the same as 3y times x. Derivative of x is 1, so it's just 3y. Derivative of a constant is 0, is 0. Now, at the point when x equals 4 and y equals -5, that's what that says, we get 2 times 4, 3 times -5, 8 minus 15 equals -7. So the partial with respect to x is -7. Let's do the same thing now with the partial with respect to y. Write down the equation. At the point 4, -5. So here, now we only look at the y values. X's are all constant, so that's a constant. Derivative of a constant is 0. Down goes. The derivative of 3xy, derivative of y is 1, so it's just 3x. Derivative of y is 1. Now it's at our point 4, 5. So anywhere we see an x, we put a 4. Anywhere we see a y, we put a -5. So 12 plus 1 equals 13. So there's our partial with respect to y. Again, it's the same thing we did in implicit differentiation, but we don't have to put dy dx after it. If we had a z, because remember, z is equal, since we only have 2 variables, if we took a derivative of z, then we have to put a dzd, whatever behind it. So another example. Find the partial of f with respect to y of the function. So z is equal to y sine xy. We're taking with respect to y. That's what it says. Now, this is a product rule. So our product are made up of these 2 parts. So the derivative of y is 1 with respect to y. The derivative of sine xy, this is a chain rule. So we have the derivative of sine is cosine times the derivative of the inside. Derivative of xy is simply x. So it's x cosine xy. So it's sine xy times 1. Since it's a product, it's plus y times x cosine. Xy cosine xy. So there's your dy or df dx or dy df dy, a partial with y. It's just, again, it's nothing really new. It's just the way we look at it now. Another one, a quotient rule. Here we have to find dx and dy. Now, fx, let's do that one first. So we're taking this function with respect to x. We have the numerator, which is 2y. The denominator is y plus cosine x. The derivative of 2y with respect to x is 0, but it's a constant. Derivative of y plus cosine x. Derivative of y with respect to x is 0, that's a constant. Derivative of cosine is negative sine. So this times 0 is 0 minus the negative, so it's going to be 2y sine x divided by y plus cosine x squared. So there's our first one. Now let's look at the function with respect to y. The numerator is 2y. The denominator is y plus cosine x. Derivative of 2y is 2. Derivative of y is 1. Cosine is a constant, so it's 0. So I have 2y plus cosine x minus 2y times 1 all over y plus cosine x squared. Distribute that. 2y plus 2 cosine x minus 2y, y plus cosine x squared. The 2y's cancel. So fy is 2 cosine x, y plus cosine x squared. So again, it's the same as we did with implicit differentiation. All right, let's do the next example. All right, now, since we only have two variables, we really have our function is really like this. So now, whenever we take a derivative of z, which we have to now, that's what we're saying here, we have to write dz, and in this case, it's going to be dx. Because that's what we're looking for. We're looking for dz dx. So y times z ln z equals x plus y. We're taking it with respect to x. So the derivative of this one, y is a constant, leave it alone. Take a derivative of z with respect to x. We get dz partial dx. The derivative of ln z is 1 over z dz dx. The derivative of x, since we're looking at with respect to x, the derivative of x is 1. Derivative of y is 0. Since we're looking for dz dx, we can factor those out. Go ahead and simplify that. So it's dz dx. You get a common denominator, so we have z over z. So it's yz minus 1 over z. multiply both sides by the reciprocal. Z's cancel, those cancel, so we have partial z over partial x. And there's our answer. Okay. So again, it's implicit because we're looking for the derivative of the actual function with all variables included. So that's why we have to include the dy or dz dx in it. Plane x equals 1. So at 1, there's a plane. Intersects the paraboloid z equals x squared plus y squared. It's not a sphere, but a paraboloid. Why is it not a sphere? Because it doesn't equal something squared. It would be a sphere if it was z squared equals x squared plus y squared. But since z is not squared, this defines a circle, but as the circle grows, it looks like this. At the point 1, 2, 5. So x is equal to 1, y is equal to 2, z is equal to 5. Find the slope of the tangent to the parabola at that point. So to find the slope, what do we have to do? Well, since we said we fixed x as being 1, we could go ahead, since x is defined as 1, we could just go ahead and say 1 and then take the partial of z with respect to y, which is 2y. The partial of z with respect to y, and y equals 2. So we could have done it that way, since we already defined what x was. Or another way, since x is defined, we have to differentiate with respect to y. So the partial of z with respect to y, z disappears, so we have dz dy. X squared is a constant, it becomes 0. Derivative of y squared is 2y with respect to y. Again, it's when y equals 2. So we have 2 times 2 equals 4. It gives you the same answer, but you could choose the method you want to use to solve it. So far, so again, it's the same stuff we've been doing since calculus 1, calculus 2. And we just take the partials of it, but we'd have to put dz dx or dx dx. Let's look at one that has more than 2 variables. Now we're doing it at 3 variables. This one won't be able to draw because the point we'll be looking at will be at x, y, z, f of x, y, z. So it's 4 dimensions. We can't do it. So what this one says, if x, y, and b are independent variables and f of x, y, z equals x sine y plus 3z, find df dz. So the partial of f over the partial of z. we have to use the chain rule here because y is an argument of sine. So the derivative of leave x alone, it's a coefficient. So derivative of sine is cosine. Leave the inside alone. Times the derivative of the inside with respect to z. So we have 3x cosine y plus 3z. As you can see, the chain rule is pretty popular in this. Here's an application problem. If resistors 1, 2, and 3 ohms are connected in parallel to make an R ohm resistor, the value of R can be found with the equation 1 over R equals 1 over the resistant 1, 1 over the resistor 2, 1 over the resistor 3. Find the value of the partial R over partial R2. We're looking for this one. When the resistor 1 equals 30 ohms, the resistor 2 equals 45 ohms, and resistor 3 equals 90 ohms. Now, what this means, since they're in parallel, as electricity goes through here, the amount of electricity gets split up respectively through these three. 30 ohms goes to the first, 45, and then 90 to the third, and then it continues its loop. So if any one of those would break, or if it's overloaded by that, then the system, one of these would short out and the system would stop. So we're looking for dr partial with respect to the second one. So we have 1 over R equals 1 over R1, 1 over R2, plus 1 over R3. We're taking both sides partials with respect to R2. So this one here, the derivative of this one, since it's on the bottom, we bring it up on top. The derivative is -1 R -2. So it's -1 over R squared divided by partial of R2, which becomes -1 over R2 times partial R over partial R2. Now, take each of these with respect to R2. This is a constant, it goes to 0. This is a constant, it goes to 0. So the only one I have to worry about is the middle one. So the derivative of this one with respect to there. Oh, it's partial, not 2. Yeah. Again, this one becomes R2 to the power -1. bring down the power. So it becomes -1 over R2 squared. There's a denominator. I put up on top, so I change it to -1. There's a derivative. I got to solve with a partial R over R2. They both have negatives, so they cancel out. Multiply both sides by R squared. So my partial R over R2 is equal to R squared over R2 squared. Now, let's say find the value. So we have to look for the value, not just for that. It tells us that R1 is 30, R2 is 45, and R3 is 90. So our next step, this is 1 over R equals 1 over R1, 1 over R2, 1 over R3. We have to find the values of R and R2. R1 is 30. R2 is 45. R3 is 90. So common denominator of all these is 90. Two times 45, 3 times 6 over 90. 2 goes in both of those. 3 goes in 6 twice. 3 goes in there 30, which is 1 over 15. So R is equal to 15. R2 equals to 45. So we have to use this formula here. R squared over R squared 2. So 15 squared, 45 squared. Fifteen goes to 15 once. One over 9. So that's what we're looking at there. Again, all it is application, just plug in the numbers, solve what we're looking for, as we're dealing with reciprocal functions, just change the signs of the exponents. Partial derivatives and continuity. A function f of xy can have partial derivatives with respect to both x and y at a point any point actually. Without the function being continuous. There. Unlike functions of a single variable, where it had to be in order to be continuous, had to have derivative, had to exist everywhere, and vice versa. Where the derivative had to exist to be continuous. That's what the definition of the limit told us in calculus 1 and 2, is in order for a single variable function to be continuous, it had to have derivative at each point in the domain. But now rules change. If the partial derivative of xy at any point are continuous, throughout the disk, the xy disk, centered at the XOYO, then F is continuous at that point. That's the caveat. If the partial derivative of f of x at any point on the curve of the disk are continuous throughout the disk centered at x00, then f is continuous at that point. So it doesn't have to exist in one point, it could be any of those in that disk. Why is it a disk? First off, okay, now let's recap that. Why is it a disk? Because we refer yesterday's notes about the interior versus bounded. So if we had a region and we had a point XOYO, there's a disk around that, so it's interior. If any of those points are differentiable, then the whole thing is. It's on the same disk. This is a pretty complex one. Let f of xy equal, it's a, anyway, if it's the function 0, if x times y is not equal to 0. It's 1 if x and y equal 0. So find the limit of f of x as xy approaches 0, 0 along the line y equals x. Prove that f is not continuous at the origin, and show that both partial derivatives fx, fy exist at the origin. This is what it means. So this is our x and y plane on the bottom. If x and y does not equal 0, then it's on that plane. If it equals 0, that means it's on the axis. If either x equals 0 or y equals 0, which is the axis, then it equals 1. That's what that crosses up here. So this is the one that says x, y equals 0, because it's on the axis. On this one, x equals 0, and doesn't matter what y is, it's 0, and likewise There. Anything else? XY does not equal 0. So let's look at A. F of XY is 0, XY not equal 0, 1, XY equals 0. We could look at it as a limit or a derivative, but it's asking us to find the limit. So the limit as X and Y go to 0, 0, F of XY equals the line Y equals X. So it says here that Y equals X, Y times X. If it equals 0, it's 1. If it's not equal to 0, it's 0. So the limit is equal to 0 as XY goes to the origin, 0, 0. That's where they're both heading towards. If the limit of 0, then it's 0. Remember, this tells us why it's not continuous at the origin, because the limit as X and Y go to 0, it's 0. But the graph in the function, this is what B part says. As X, Y go to 0, 0, on the graph, it's heading towards 1. As X and Y go to 0, it's 1. That point there, not down here. In order to be continuous, the limit has to exist. It does. The point has to exist. It does. And they have to be equal. Since 0 does not equal 1, it's not continuous at 0, 0. Again, in Cal 1, we defined limits. For a limit to exist, you have to add 3 things. First, the limit has to exist. Check. At 0, 0. 2, the point has to exist at that point. It does. It's 1. And then they have to be equal, and they're not, so that takes care of that. They show that both partial derivatives f of x, partial f, partial x, and partial exist at the origin. Got to do the third one. So first, to find the partial of f and the partial of x at 0, 0, since we're looking for partial of x, we fix y equal to 0, because that's the point we're looking for. So x times y is equal to 0. Well, according to the chart, if x times y equals 0, then the function f of x, y equals 1 for all the x's. And likewise, we do the same thing with df, dy. In this point here, we set x equal to 0. So the product x times y is 0, which means that if f and x are 0, then the answer is 1. Let me see what else it asks us to find. So they both exist. And they both exist. All right, so everything we've done so far are first order differential equations. Second order partial differential equations. First, we've done this. And so on and so forth. Now we're going to look at something like this. This is the same thing as saying fxx, or second derivative. This is the same thing as saying fyy. Or we can have mixed. We can have the partial of f, the partial of x, partial of y. That's the same thing as writing yx. Or the partial of f, partial of y, partial of x, which is the fxy. All these mean is we're taking multiple derivatives of the denominator function. X squared and y squared, that means second derivative, both times with respect to the same variable. It becomes more complex once we get to the mixed format. What this one says, if it's xy, we're reading this way. Or if it's fx, because what we're doing here, we'd first have to take the derivative partial with respect to y, and then the partial with respect to x. This one, we take derivative with respect to x, and then the partial with respect to y. So we have to first find the first derivative with x, then the second derivative with respect to y. So it's very, very, very important on how you read those. So if we have dx, dy on the bottom, we do dy first, then dx. If we have dy, dx, we do dx first, then dy. If it's given this way, we read y and x, we work our way out. So we do that, and then we do that. All right, so let's look at an example here. If f of xy equals x cosine y plus y e to the power x. Find the second order derivatives, all of these. All right, the first one. It's a second order derivative of f with respect to x twice. So the first thing we have to do is we have to find the first partial derivative with respect to x. The derivative of x is just cosine y. Again, fix y as a constant. So the derivative of ex is the derivative of e to x is ex. So it's just y e to the power x. Now we do the second partial derivative with respect to x. So the derivative of this one is 0. The derivative of this one is y e to the power x. So y e to the power x. Yeah. So that's the second derivative there. Let's look at the second one. Partial of dy dx. So what this one says I have to do first. What's that? No. So we have to do what first? Yeah, we're doing this one next. So we do the x first. So there's our function. Our derivative with respect to x is cosine y plus y e to the power x. Now we take this is our function. Now we take the second derivative with respect to y. Negative sine y plus e to the power x. There's that one. So that's the second derivative. The third one. So we take the partial with respect to y first, which is negative x sine y plus e to the power x. That's the first one. And the second derivative with respect to y again, we derive this one with respect to y. So derivative of sine is cosine, so it's negative x cosine y, and that's a constant, goes away. So there's our second derivative. And the last one, d. dx dy. So we do dy first. That'll give us negative x sine y plus e to the power x. Then do this one with respect to x. Which makes it negative sine y e to the power x. These four examples, two of them show something special. A French mathematician, Clairaut, found that it's the order in which we do higher order partial derivatives is irrelevant because the commutativity works in there. We take partial of yx, we got this, negative sine y e to the power x. Or if we did partial of xy, we got the same answer. So when you do mixed partial derivatives, it doesn't matter the order you do it. You can choose whatever method you want because it'll give you the same answer at the end. So So that is an important finding. Because it makes life much easier for us. So let's get this. Find the second partial derivative of w with respect to x, y. So we'll do it both ways and see if we get the same answer. So according to this, the first thing we have to do is with respect to y. So fixed x derivative of y is just x. Now this is a quotient, so we have e to the power y squared plus 1. Derivative of e to the y is e to the y. Derivative of this one is 2y. This times this, so it's y squared plus 1 minus this times this, 2y all over the denominator squared. And then we go on, see if we simplify this any. Y squared, no. Nope. So part B would be the second derivative would be with respect to x. Since here all of these are functions of y, those are all constants, they disappear, so we get 1. The derivative of x is 1. Let's see if we would change the direction. So if we did dy dx, so partial of w with respect to x first would just be y. The derivative of all this stuff is gone. Then with y, it equals 1. So we see that it doesn't matter which one, but it would have been easier if we did it this way first. Because since this whole second part is with respect to y, we take a derivative with respect to x, all that disappears. Okay. Higher order partial derivatives. We're not limited to just 2. If we did 3 derivatives, okay, so you can ask the partial derivatives in any specific order you want, or any combination you want. Now, if I gave it to you in this format, another way we could have written it makes it much easier, because a lot of times you get confused that these look like 2's instead of d's, partials. Since we're dealing with a partial derivative of the function w, we're doing z, y, x. This one is a w with respect to y, x, x. Remember, the directions are opposite. If it has the partials, we're reading, do this one first, this one second, this one third. If we have as subscripts, we do this one first, second, third. So y, x, x, y, y, x. So how would this one look if I was to rewrite it? Now, with the argument I just gave you against me, saying, yeah, why worry about it? Because remember, it doesn't matter how we integrate them or derive them. But if you're going to do straight up, this is what it means. But it really doesn't matter how you arrange them. As long as you take two partials with respect to x and two with respect to y, it does not matter. Last example, then we'll call it a day. So I have to go back and fix sections 4 and 6. I don't know what's wrong with those. All right, here it says find partial of y, x, y, z, if this is the function. So f of x, y, z is equal to 1 minus 2x y squared z plus x squared y. So the first one's asked, this one's asking for is f of y. Fix x and z as constants, so that's gone. 1, 0 is gone. Derivative of y squared is 2y, so it's 4x, y, z. The derivative of y is gone, so it's x squared. That's the first one. The second one, now with respect to x. Derivative of x is negative 4yz plus 2x. Treat everybody else as constants. Third x, no, it's y, x, y again. So derivative of y is 1, so it's negative 4z. That's a constant, so it disappears. Y, x, y. The last one we do is with respect to z. So it's negative 4. But there you have it. This is why this is one of my favorite topics to discuss, the partial derivatives. All right, so that does it for section 3. I have to fix section 4 and 6. Everybody, we have a question. I hope it helped. I hope today was an easy, quick lesson. So you're very, very welcome. Okay, everybody. I will see you all tomorrow. I'll also start putting up other lessons because I forgot that this section has a whole bunch of them. I'll tape those and put it out there. It's just that I don't want to keep you all here for 6 hours in one time. So I will do that and we can finish up chapter 4, hopefully before next week. because we're getting close to the end of the semester. All right, have a great day. Thank you. You're very welcome.